The next concept that we will be visiting right now in the hydrogen atom problem is called the Zeeman effect. What is Zeeman effect? It is when you subject an atom to a constant external magnetic field, what changes come about is what we were going to take a look at. Before we go there, we will have to review some concepts of what is a magnetic dipole. A dipole is one where when a charge ends up moving in a certain direction, uh, let's say you have an electron that ends up rotating in a given direction, you end up creating a dipole moment that's given by mu. This is given by the product of the current times the area in which this charge ends up moving around, right? For instance, A is the area of the loop. Let's say that you're thinking of an electron that is moving in this direction. Basically, you're talking about the charge on this to that area that is actually present. A little bit of review from your physics classes would remind you where the current will be given by something like the product of the charge to that of the velocity of the particle, in this case the electron, let's say, and to that of the area. Area for a circular unit will be given by pi r square. So this immediately reduces to something as 2rv qrv divided by 2. In this case, we just took an example of a circular motion, but let's say you have different types of motion that ends up happening. Non-circular, for instance, or something like an ellipse. Then this magnetic moment dipole will be given as q by 2 times r cross v. Okay, so this is also a vector that ends up coming. The important aspect that one has to recognize here is that the r vector and the v vector are in certain direction, and the mu that ends up coming is perpendicular to both r and v. Okay, this is an important thing. This, once again, we would have learnt back in our physics classes, where if an electron goes around rotating in a circular orbit, you start making magnetic dipoles, meaning that one end of it behaves as the north pole, the other behaves as the south pole, right? That's the same concept we are borrowing back here again. Okay, so now having seen this, if you pay close attention, you are able to recognize the fact that the mu has an r cross v component. A little bit of recollection would make you remember that the angular momentum is given by the product of r cross p. The only difference between the equation that we see here and the equation that we have seen just a moment ago for the magnetic dipole moment is that it's an r cross v versus an r cross p. So the simple manipulation that one could do is to take the mass and then get an r cross p. So we are able to understand here one of the very important conclusions: the magnetic dipole moment goes along with the angular momentum vector. So this is a very important connection for one to do. Basically, the angular momentum vector and the magnetic dipole moment are collinear to each other, such that the magnetic dipole moment is perpendicular to both the r and the v vectors that are present. Okay, good. So far so good. Now, having done this, if we are trying to think of an electron as our entity, then this equation would end up becoming minus mod E, where E is the magnitude of the charge divided by the mass of the electron times the angular momentum vector. Very good. So now, having seen this, the next aspect that we need to think about is that how does the Hamiltonian change in this case? The Hamiltonian, let's say, will be given by h0 times h1. The Hamilton as a sum of Hamiltonian, which is the Hamiltonian in the absence of any field, and the Hamiltonian due to the presence of a magnetic field that we have set this atom in. So this is important mainly because how does this energy go? So the energy, when a magnetic dipole is present in an external magnetic field, will be given by minus mu dot b. Okay, these two are also vectors. This is the magnetic dipole moment vector, while this is the external magnetic field that has been applied. Right? So now, having done that, one is able to appreciate the fact our Hamiltonian, the unperturbed Hamiltonian, is having an additional effect due to the magnetic field B. Okay, let's say that we apply the B field only along the z axis. So let's say it's given by B naught is given by Bz times k cap, and you had mu in the previous page where mu is given by this given vector minus mod E divided by 2 me minus mod E given divided by 2 me times L cap. And you might remember L cap is Lx I cap plus Ly j cap plus Lz k cap. So the moment you have something of this sort, you have a dot product, immediately the Hamiltonian one will be nothing but mod E divided by 2 me times L cap dot B cap. Since only the z component exists for the B cap vector, this is going to get reduced to this form, 2me Bz Lz, right? So Bz is the magnitude of the external field that is being applied, and Lz is an operator which we know as minus IH cross dou by dou phi. Okay, so now having done this, we are able to appreciate the fact. Let's go back to the Hamiltonian that we started with. So you're going to have something like the Hamiltonian that's given as the unperturbed Hamiltonian minus mod E by 2me Bz times Lz. When we solved the eigenfunctions of the Hamiltonian operator for the hydrogen atom problem, we got something like psi nlm is given by rnl times ylm, right? And one is able to quickly understand the fact that this is independent of the m quantum number, while this is dependent on the m quantum number. So what ends up happening now is that once you apply, this ends up when you operate the Hamiltonian on psi nlm, you are going to get whatever you got for the eigenvalue of energy, so which is going to be minus E square by 8 pi epsilon naught A naught n square, where n is the quantum number. And then when you apply this on psi nlm, you're going to get something like minus mod E by 2me Bz Lz operated on psi nlm is going to give you m h cross psi nlm, right? So therefore this is going to be nothing but h cross times m value, giving back psi nlm. Okay, so that's what we end up getting as the final sum. So this is important to understand, where previously the energy was not dependent upon any quantum number apart from the n quantum number, and now we start to understand that it also gets perturbed based on the m quantum number. Okay, so now what does this finally cause? Let's rewrite this equation so that we simplify it in a manner. So this will become something of the sort E is given by minus E square. Okay, there's a subtle mistake that has happened here, where when you have minus mu dot B, the minus sign that ends up coming will get changed to plus. This is going to be a plus, this is going to be a plus, this will end up being a plus. Okay, so now when we have this equation, let me write it carefully, where this is going to be 8 pi epsilon naught A naught plus mod E times h cross divided by 2me times Bz times the m quantum number, right? Let me be careful. In the presence of B field along Z. We choose the Z-axis because the representation of the angular momentum is the simplest in that case. So we end up choosing that. So now when we see this, what is one able to understand? This is a constant, and this constant will be defined as beta, and its value is equal to 9.274 times 10 to the power minus 24 joule per Tesla. It's given joule per Tesla so that how much ever magnetic field that you end up applying will perturb this. And an important thing, we can also convert it to EV per Tesla so that one is able to understand what is the magnitude that ends up coming, because you're talking about something like 13.6 EV by n square. right? So you're having such a contribution. So now what might end up happening here? One is able to appreciate you're having a 10 power minus 19 that will go. So you're still having something like 10 power minus 5 EV per Tesla of that sort, probably 10 power minus 4. So this is really small effect as compared to the energy difference between the different wave functions that come for various values of n. However, this is not a small effect that comes into play. So this does indeed perturb the entire system. Let's try to draw the 1s orbital. And then you have the 2s and 2p, which will have the same energy because you're talking about minus 13.6 by 2 square, while this is minus 13.6 by 1 square, that this contribution just comes. So basically we are talking about a case when there is no field. Now when you subject to a BZ field, what will end up happening? Since the s orbital has an m quantum number that is 0, you're talking about y00, that remains unperturbed. The 2s orbital also remains unperturbed. I'm going to write the 2p orbital a little farther away so that you can see what ends up happening. Then you have the 2p orbital which has one component which is L equal to 1, M equal to 0, that is also unperturbed, right? So these two are degenerate to start with. So let's think about which one will be having a higher energy. You're looking at a term where positive ends up coming. So if you have an m value that's going to be positive, that is going to be greater in energy, and if you have an m value negative, it's going to be negative times a positive that overall reduces the total energy. That results in a case of this sort. In the molecular spectroscopy course, you will be introduced to the topic of something called selection rules, which I'll not be going into detail. It just suffices right now to say that you will only have transitions that end up going from 2p to 1s, in which case previously you had a single transition that is going to happen, you're going to get a single line. On the other hand, you're going to have transitions from this state, and also from this state. So this results in 3 resonances that you will end up observing. So you go from a singlet state to something like a triplet state. So this is the overall influence of an external magnetic field when atoms are subjected to them. Okay, so this gives a way of also finding out what is the L quantum number that you are trying to probe in each of these cases. So this would help for you to further understand what happens when people get atomic spectra using different techniques. Okay, now having understood this, although we spent quite an amount of detail trying to understand the change that comes from a singlet to triplet state, the interesting thing is that experimentally you see more than a triplet. Okay, so this is intriguing by itself, and in order to understand this, you need to be introduced to another concept called spin angular momentum. Okay, and this comes up because of the fact that electrons by themselves have an intrinsic spin that is associated with them. The electron is basically a gyroscope by itself. When Stern and Gerlach did their experiment in order to find properties of the electrons, they actually took silver atoms and they subjected the silver atoms across a magnetic field. One might ask, why did they choose silver atom? Because it has a favorable phi s1 type of an electronic configuration where you have a single electron in the s orbital, and having just learnt the Zeeman effect, when you are having L at 0, this is not going to be perturbed. So basically you are going to get a singlet line that ends up coming. On the other hand, when they tried to subject it, what they were able to see is that they ended up getting a doublet. And this is once again a little difficult to understand because in the previous example, we were able to see a triplet. So we had 3 lines, and that goes as 2L plus 1 equal to 3, which indicates L equal to 3 minus 1 by 2, which is 1. So it makes sense. L value was 1. On the other hand, in this case, you are seeing a doublet. So what does this doublet indicate? You have 2L plus 1 equal to 2. This immediately indicates L equal to half. So this is a little difficult to understand. So far we have seen cases where L is 0, 1, 2, 3 and so on, and never a half integer value that you end up seeing for the electron in this case. And similarly, other experiments that were done with alkali metals like sodium, potassium, and lithium and other ones also showed similar behavior. This meant that it's not a isolated observation. This observation is indeed seen across a bunch of different atoms. This indicated that the phenomenon that they are observing with a doublet in the presence of a magnetic field is a fundamental property and is not unique to silver atoms, was the conclusion that was made. In order to explain these effects, in 1925, Wolfgang Pauli came up with this proposal that the electron can live in two distinct states. Okay, so this was able to explain things in an ad hoc manner. If you might realize, we started with the wave equation that explains everything in an ad hoc manner. Then he introduced a spin quantum number m, which can go between 1/2 and -12 for the electron. Basically, it's ms for the electron, spin quantum number that can go between +12 and -12. However, Pauli did not give any explanation for such a fourth quantum number. So the other three quantum numbers that we have seen are principal, azimuthal, and the angular momentum quantum number. Now the ms is what is being proposed. It was later in 1925 where two other scientists, Uhlenbeck and Goudsmit, ended up describing this to be the spin states that are present. So basically we saw how these three quantum number came up when you were able to imagine h psi equal to E psi, when yet another assumption was incorporated into this, the spin quantum number comes to it by itself. So that will not be discussed in the current class, but this is enough for us to understand there is yet another quantum number that goes with it. Okay, and since we are able to realize that this is very similar to the angular momentum, all properties of the angular momentum quantum number gets associated with this as well, meaning that when you have L square operating on YLM, you ended up getting h cross square L into L plus 1. Similarly, you have an S square when operated on spin comma ms will give you h cross square S into S plus 1, S into ms, okay, where S is the spin quantum number. And spin quantum number for an electron is half, right? And similar to this, you have the LZ operator, which when operated on YLM gives you h cross m times YLM. So similarly, you have an SZ operator on SMS, h cross ms times SMS. And of course, the other properties that we had discussed exist here as well. The commutator relationship holds good, and then you have something like Si times Sj is I epsilon ijk Sk, where this is +1 for cyclic and -1 for acyclic. Okay, so all these properties hold good, and interestingly enough, they were able to attribute when you have a spin quantum number of half, you have ms that goes between plus s to minus s and one integer step, so there's going to be plus half and minus half that are going to be present. They started associating the plus half spin to the alpha state and the minus half spin to the beta state. Okay, so for instance, if you are operating s square on the alpha state, you are going to end up getting h cross square half into half plus 1, half comma alpha back. Of course, I should have written a half here. And similar is going to be the result when you're operating s square on half comma beta. Beta is the minus half spin. So remember the s remains constant. So both are going to be half into half plus 1. Half, of course, you get beta back here. So in this case, what ends up happening, the prefactor in both these cases is going to be h cross square times 3 by 4. So you end up getting something like this. On the other hand, when you apply Sz on half comma alpha, you're going to be getting half h cross times alpha, and Sz on beta is going to be minus half times beta. For the sake of simplicity, I'm not going to be writing half comma alpha or half comma beta anymore. I'm just going to be referring this to alpha, and referring this to beta, since we are associating only with the electron spin right now. Okay, so now one is able to understand that these two states exist and their relationship is very similar to that of the eigenfunctions that you have seen before for the spherical harmonics, where alpha and beta are the orthonormal basis set, meaning that integral of alpha to alpha will be equal to 1, same with the integral of beta to beta. On the other hand, any cross integral of alpha to beta or beta to alpha will be equal to 0. Of course, once you subject these two energy states which are degenerate in the absence of a magnetic field, let's say there is no magnetic field that's applied here, the moment you set them in an external magnetic field, what is going to end up happening? You're going to have a splitting that will come up, which will once again go with the energy that's given by minus mu dot B. And you might remember the mu that you had is the dipole moment. These are also dipoles by themselves. So they do exert magnetic properties. And the dipole, you might recollect right now from the Zeeman effect, where you had something of the sort Q by 2 times R 2m R cross B. Okay, so this is its own, let's say, mu e for the electron, and this is the angular momentum that will end up coming for the spin of the electron. So the Zeeman effect happens wherever you have the spin quantum number that exists for an electron. So therefore, when you subject an electron to an external magnetic field, they have two different non-degenerate energy levels, and as you will soon learn, when you have two non-degenerate energy levels, you can always transfer populations from one state to the other state in order to get a spectrum. You plot intensity as a function of energy and you get resonances, where in resonance means there are two energy levels that are interacting with one another with the help of electromagnetic radiation. So this is one of the important techniques, because people use this in something called electron paramagnetic resonance. And one important thing that we have to realize is that the wave functions that you now ended up getting, you had N, L and M, now will get updated with N, L, ML and MS that's going to be present. And luckily, in our case, it's going to be NLM times the alpha state that you ended up having or the beta state that you ended up having, depending upon the spin quantum number that is present. Okay, so this makes our life easy, because if you want to integrate throughout space, where if you are having integral of the spin state and the wave function that has a radial and angular part, this is quite easy to do, because you can separate them and integrate them separately, and using the identities that you have learned before, it's going to help you out solve the integral that you're having. And without going into any further details, similar to the electron having a spin, even the nucleus could have a spin. Okay, and this is largely because the nucleons are also packed in their own orbitals. And the moment you are having some unpaired nucleons, that could result in a spin that arises, the nuclear spin also is associated with a spin angular momentum. And unlike the case of an electron, where you have a spin half, nuclear angular momentum can be n by 2, let's say half, 3 by 2, 5 by 2 and so on. They can also be integer units, they can be 1, 2, 3 and so on and so forth. And the moment you realize this, you are able to understand the fact the spin half system behaves like the electron, and many nuclei such as proton, carbon 13 and 15N are all spin half nuclei. This is why they end up being an even 31 phosphorus, 19 fluorine. These are very common nuclei that end up having a spin half, and this is what results in the nuclear magnetic resonance spectrum. This means that if these isotopes are present in your molecule, when you subject them to an external magnetic field, they end up splitting, and therefore you can use radio frequency waves in order to understand how the molecule looks. So this is a very common type of fingerprinting technique that's routinely used by chemists. So is EPR. Whenever you have a lone electron that ends up being present, for instance, whenever you have a case of a nitroso ion that is being present, the lone electron helps you identify their presence when you subject them to EPR. Similarly, these kind of nuclei help you in NMR. So as much as we have seen, particle in a 1D box helped you understand conjugated systems, and when you had harmonic oscillator that helped you understand vibrational systems, and the rigid rotor that helped you understand rotational systems. Now you are looking at an example where, of course, the hydrogen atom helped you understand the atomic spectrum, as you will learn in the molecular spectroscopy course. The spin will help you understand EPR and NMR that are present. And one important thing that I missed to say here is that all these are singly degenerate. There is no degeneracy that comes up here. So are all these states. So all the spin states are singly degenerate, right? Of course, in the presence of a magnetic field. In the absence of a magnetic field, each of the spin state that is being present for spin half, it's going to be doubly degenerate because both the energy states have no distinction in terms of their energy. So I hope this lecture has been helpful enough for you to understand how to apply quantum mechanics to a system such as the hydrogen atom, understand its wave function, and proceed towards understanding intricate properties of the atom such that they can be exploited in order to perform EPR and NMR experiments.